Hey everyone, today we're going to be continuing our mobile robot build by looking at the concept design. We'll start off by looking at the differential drive concept and how that works, and then we'll spend most of the video focusing on creating a URDF file for our robot. This is a file that tells Ross about the structure of our robot and how it's all set up. The next step after that is going to be to drop it into Gazebo and drive it around in a simulation environment, but unfortunately the video is getting a bit too long, so I've cut it short and that's going to be in the next part. Let's do it! The robot we're building is called the Differential Drive Robot, and that means it's got two driven wheels, one on the left and one on the right. Those two wheels are responsible for all of the motion control of the robot, and any other wheels that it has are just there to keep it stable. Those other wheels can spin freely in all directions, and they're called caster wheels. Now this kind of arrangement, the Differential Drive Robot, is pretty common. You'll find it a fair bit, and that's for a few reasons. It's easy to understand and control and build, and it also means the robot is pretty nimble because it can turn around on the spot, unlike something like a car that needs space to do a U-turn or a three-point turn. Differential drive robots can come in a variety of shapes and sizes. One of the most popular ones that you'll see with Ross for education and research is the Turtlebot. That comes in a couple of different models. But for today, we're going to assume that our robot looks something like this. A small box with the driven wheels near the rear and a caster wheel near the front. We'll take a closer look at the chassis design in a future episode. Also, speaking of the Turtlebot, thanks to Everluke on Reddit for this gem. Now, controlling differential drive robots with Ross is a topic for a whole video in and of itself, and we'll look at that down the track when we see how to integrate the ROS 2 control libraries. For now, there's only two things that we need to know, and they're both set out in the ROS standards. Firstly, that the main coordinate frame for our mobile robot should be called baselink, and secondly, that the orientation of this coordinate frame should be X pointing forward, Y pointing to the left, and Z pointing up. We're about to start making our URDF, and so I'm going to assume there's a few things you've done already. You've installed ROS, you've copied the package template from GitHub, you've created a workspace on your computer and built it with Colcon, you've installed Exacro and Joint State Publisher GUI using the commands on screen, and finally, that you've already watched my other tutorial videos on transforms and URDFs in ROS. I do really recommend you watch those first, but if you haven't, here's a quick recap of some of the most important things. We start with a bunch of configuration files written in the URDF format that altogether describe the structure of our robot. These files then get processed by a tool called Exacro, which combine them all into a single complete URDF. This gets passed into another program called Robot State Publisher. Robot State Publisher then makes the URDF data available on the robot description topic, and it also broadcasts the appropriate transforms. If there are any joints that need to move, Robot State Publisher will expect to see the input values for those joints published on the Joint States topic. And while we're doing our initial testing, we can use the Joint State Publisher GUI to fake those values. And to make life easier, we typically wrap all of this up into a launch file so we can run it over and over again. Before we start creating our URDF file, there are three things that we should be aware of when we're saving our changes. Firstly, when you're building your workspace with Colcon build, if you use the symlink install argument, then you won't need to rebuild every time you update the URDF. It'll handle that automatically, except for whenever you add a new file. That file needs to get built and copied once, and then after that, it'll be kept up to date. Secondly, every time you make a change, you're going to need to quit and relaunch Robot State Publisher so that it has a chance to republish the topic. And thirdly, when we're visualizing our URDF with RViz, sometimes it won't pick up all your changes straight away. In this case, you usually just need to hit the reset button in the bottom corner. If it's still not updating, you can try ticking and unticking the display items, and if that doesn't work, you can just close and reopen it. So now it's time to create a URDF for our robot. Okay, so I've fired up VS Code and I've opened up my workspace, and you can see here the package that we made in the last tutorial. So mine was called Articubot1, yours might be called MyBot or something else. And if you copied your package from the template on GitHub, then we should have these directories here, and we can see in the launch directory, there's this file rsp.launch.py, and then in the description directory, there should be this file here, robot.urdf.exacro, and all it is a very simple Exacro file with just an empty base link in it. So first up, we're going to have a go at running that launch file. So get into your workspace and make sure you source it. and then we're going to type ROS2 launch the name of your package. So in my case, it was Articubot1, it'd be whatever you've got, and then rsp.launch.py. Now, I'll put this over here. You can see this is running, it's run robot state publisher, and it's found the one link there, that's the base link that we had in here. Now, I'm not going to fire up RViz so we can take a look yet, because there's nothing to see. We've only got one link and it's empty. Once we've added some more links, we'll open up RViz and we'll be able to see some things. Now, for this robot, we're not going to keep all of our stuff in this single URDF file. Instead, what we're going to do is we're going to split it up over multiple files and include them all in here. So in this video, we're going to be creating one file that will be for the core structure of the robot, and then in the future, we can create ones for the LiDAR, the camera, and so on. So open up robot.urdf.exacro. You can go ahead and delete that link that we've got there, and we'll replace it with exacro include file name equals robot core.exacro. Now, if we were to try and rerun robot state publisher now, it's going to fail because it's trying to include this file robot core.exacro that doesn't exist. So we better make it. In our description directory, we can go create new file and call it robot core.exacro. And we've got to make sure it's a valid URDF file. So we'll start by copying and paste everything from the main one, and we'll put it in this one. We'll delete the include and delete the name because we don't need that. We'll also tell VS Code that it's an XML file so that it can highlight things for us. All of our links and joints and everything are going to go in here, and we'll step through them all one by one. Now, just a quick warning, there are going to be some parts of this tutorial that might get a bit confusing if you're not used to doing geometry and mathematics and spatial sort of things. That's all right. If you find those bits hard, just copy and paste what I do, push through, and hopefully it'll make more sense in hindsight. Now, before we go ahead and make any links, what I'm going to do is I'm going to set up some materials or colors. I mentioned this in the URDF tutorial. With URDF, what we can do is we can set up all of our colors that we want to use up front, and then every time we're making a link, we can refer to that color by name. Now, if you're familiar with the format that I'm about to use, you can go ahead and make your own colors. If not, that's all right, just copy the ones I'm going to do. Now, I'm going to be putting them just at the top of this robot core.exacro file. It'd probably be better to put them in another file that you can include in here, but for now, I'm not going to worry about that. So I'm just going to set up the first color here. So we'll go material, name is white. And then the rest of the colors I've already prepared earlier. I'm just going to paste them in here. So now it's time to start making our links. Now, like I said before, it's the standard in ROS when you're working on a mobile robot for the first link to be called a base link. So I'm going to go link name equals base link. And that'll do for that one. Now, where's the base link sit on our robot? You might think that the natural place for it to be would be at the center of the chassis somewhere, and that wouldn't be wrong, but when we're working with differential drive robots, it's often easier if we have the base link set to be the center of the two drive wheels, because that's also the center of rotation of the robot. And then for the rest of the robot, we can describe it all with reference to that. So that's the base link. Next up is our chassis. Now remember, we're not going for detail here, this is just the rough structure of the robot. So I'm going to say that our chassis is a box that is 300mm wide by 300mm long and 150mm high. For our American friends, that's roughly 1 foot by 1 foot by half a foot. And because URDF uses meters, that's going to be 0.3 by 0.3 by 0.15. So we'll start by making a joint. So we'll have our joint name is chassis joint, and this joint is going to be fixed, and the parent link is going to be the base link, and the child link is going to be the chassis. Now I want the origin for my chassis to be at the back bottom center. So that'll be sitting just behind our base link. So the origin of the chassis will be just behind the center of the two drive wheels. So we'll set the origin X, Y, Z to be just set back a little bit in X and then 0 in Y and Z. So that should set it just behind our base link. So now we need to make the actual chassis link. And inside that, we're gonna have our visual tag. And inside that, we'll have our geometry tag. And then inside that, we'll have a box tag. And like we said, the size is gonna be 0.3 by 0.3 by 0.15. Now I want my chassis to be white, so we'll go material name equals white. And we're not quite done yet. We've got one of those tricky bits now. You see, I wanted the origin of the chassis to be at the rear and at the bottom, but by default, when we put this box in, it's going to be centered around the chassis origin. And so to fix that up, we need to shift the box, shift the visuals forward by half its length in X and up by half of its height in Z. And that should put the origin where we want it to. So I'm going to go origin X, Y, Z equals, so half of the length is 0.15, then 0 in Y, and then we want to go 0.075 in Z. And that should place it where we want it to be. So let's see if that worked. Remember, first what we've got to do is we've got to rebuild because we changed a file. Then we can rerun Robot State Publisher. And we can see here now we've got the base link and the chassis link. And now we'll launch RViz. So first thing we've got to do is set our fixed frame to the base link. And that'll go okay. Then we'll add a transform display. And why don't we show names? So we can see there our base link and our chassis. And then we'll add a robot model and set the description topic to robot description. And there it is. There's our chassis. Now, to properly finish off this link, we need to add our collision and inertia tags. But what we're going to do is we're going to go through and get the visuals worked out for the whole thing and then come back and add those other bits. So the next bit we've got to do is our wheels. So first we'll do the drive wheels. Now, I might just quickly clean this up a bit. So we'll go base link. These are just comments to help us know what we're doing. Chassis link. And now we'll go left wheel link. So we'll start off by making a joint for it, and the wheel's obviously going to move, so we'll go left wheel joint, and this one's type is going to be continuous because our wheel can rotate around continuously. Now we could connect them to the chassis, but instead I'm going to connect them directly to the base link because if you remember, the whole point of the base link was that it was at the center of rotation of the wheels. So we'll go parent link is base link and the child link is one we're going to make called left wheel. Now we'll finish the joint in just a minute, but I'm going to go ahead and start filling out the link. So we'll go link name is left wheel and visual tag, geometry tag, and this one is going to be a cylinder with radius of, let's go 50 millimeters radius. So that's 100 millimeters diameter, and length of, let's go 40 millimeters length. And why don't we make it blue? Now we're about to run into a problem, and that is that in ROS, cylinders by default are oriented along the Z axis, so up and down, but we need our wheels to be oriented along the Y axis, so from left to right. And so what we're going to need to do is rotate that cylinder that would currently be going in the Z axis. We want to roll it by a quarter turn around the X axis so that it's pointing along Y. Now, a quarter turn in radians is pi on 2, and I like to keep my Z-axis pointing outwards from the robot, and it's currently pointing upwards. So according to our right-hand rule, if we want to rotate around the X-axis so that our left wheel has its Z pointing left, then we want to rotate by negative pi on 2 around X. So I'm going to go ahead and make my joint origin. Now the other thing we've got to do is our wheel is not in the center of the robot, it's got to be offset in Y off to the left. So I'm going to make it be 0 in X, then in Y it's going to be 0. Let's say 175, so 175 mil to the left of center, 0 in Z. And then for roll pitch yaw, our roll is going to be minus pi on 2, and then 0 pitch, 0 yaw. And the last thing we've got to do is specify an axis of rotation. So when we have a positive motion in the wheels, which way is that spinning? Now, we want that to be positive around Z. So anti-clockwise around Z on the left wheel when it's pointing outwards is going to be positive. So we're going to specify the axis X, Y, Z to be 0 in X, 0 in Y, and 1 in Z. And that should be our left wheel. If that was a bit confusing, that's all right. Just copy and paste, and hopefully you can figure it out later. Now the right wheel is pretty much just going to be a copy and paste of the left wheel. So then what we're going to do is we're going to have to flip a bunch of the values. So we'll just quickly change these to right. We're going to have to go onto the other side there. We want to rotate by positive pi on 2, and we'll be going around the -1 axis. Now, if we go back here and we try to rerun Robot State Publisher and look in RViz, we'll see it says there's an error. It says that there's no transform for the left and right wheels. And that's because it can't find the joint states for them. It doesn't know how much the wheels have turned. So the way we're going to get around that is by going ROS2 run joint state publisher GUI. Make sure you've got that installed. And now once that's up, we should see our wheels appear. And hopefully, when we turn the left wheel joint forward, our left wheel turns forward. And when we turn the right wheel joint forwards, it goes forwards. Finally, we need to add a caster wheel. Now the easiest way to do this is to have a sphere that's attached to our chassis with the lowest point at the same height as the base of the drive wheels. Now rather than making the sphere be able to roll in every possible direction, we're just going to make it completely frictionless so that it can slide around without causing us any trouble. It's kind of cheating, but it works pretty well. We're going to look at that later when we do simulation. That's when we'll bring in the friction. For now, we're just trying to get the location of it correct. So we'll add our caster wheel link. So this one's going to be a fixed joint. So parent link is the chassis, child link is the caster wheel we're about to create, and the origin, X, Y, Z. Now we need it to sit pretty much at the front of the chassis, and remember the origin for the chassis was at the very back. So let's go 0.24, that should be pretty close to the front, 0 and 0. So now we'll add the link. As always, visual geometry, and this one is going to be a sphere with radius 0.05. And that will match the radius of our wheels over here. And let's color it in black. So that should be our visual structure kind of done. So let's rerun. Our robot state publisher and take a look in RViz. And we can see now we've got our drive wheels as well as our caster wheel. Now the next thing we've got to do is to get the collision sorted out. Now this is pretty easy. We're pretty much just going to copy and paste what we did for the visuals, but without any material. So I'll start with the chassis here. So we'll copy and paste the visual, change that to collision, and it doesn't need a material. So I'm going to go ahead and do that for the rest of them. Now to check that we've done the collision correctly, we can rerun Robot State Publisher again, go back into RViz, and now what we can do is over here in the robot model, we can untick Visual Enabled and tick Collision Enabled. And it looks exactly the same. It uses the materials that it had for the visual one, but that's because we've used exactly the same shapes. But if we had different collision shapes, it would look different here. So I'll swap that back to visual. And the last thing we've got to do now is add our inertia. Now, as I mentioned in the URDF tutorial, adding inertia tags can be pretty annoying. And so to make that easier, I've created another file that we can include that has a bunch of macros. Now, I'll include a link in the description below for this, but for now, I'm just going to have it magically appear right here. So once that's in your description directory, we can go up to the top of this file and we'll add an include for it. So we'll go exacro include file name equals inertial macros.exacro. And now all of the macros from that file are going to be available to us. So I'm going to go ahead and add these to each link. Now, one thing to be aware of is whenever we're using the inertial macros, we have to specify an origin, and that's the origin to match this one in the visual, not the one in the joint. And so for this one, we've actually specified one, but for these ones here, for example, we didn't specify an origin, so we're just going to have to make it all zeros for that. So I'm going to go through and do them, and you can just copy them. So for the chassis, we're going to use the inertial box macro. Now we've got to specify the mass, so I'm going to make that 0.5 kilograms. So that's the box one. Now for the left wheel, we'll have exacro inertial cylinder, make the mass 0.1. Copy that to the right wheel. And the last one's going to be inertial sphere. We'll make this one also 0.1. So that should be all finished. We can rerun Robot State Publisher to check that it works, and it doesn't because we added the macro file and we didn't rebuild. So we'll rebuild that, run it again. Now you can see it's all happy. It doesn't look any different with the inertias, but it'll affect it once we start to do simulations. So that's it. That's the core Exacro for our robot. We've got our chassis, our drive wheels, our caster wheel, we've got collision, we've got inertia, and the best bit is we're ready to expand on it by just adding more and more files and including them all in here. Now, one other thing we can do is we can save the state of RViz in case we want to come back to it later. So let's go File, Save Config As. Let's find our workspace. I'm going to put it in here and call it ubot.rviz. And then if we ever want to use that again, we can run rviz with the path to source, articubot1 config ubot.rviz. And there you go. We brought it right back up where we had it. So now that we're finished, let's commit our changes to Git. Now you could do this here in VS Code using the source control section, but I'm going to do it in the terminal. So I'm going to get into our package directory. So mine's articubot1, type git status, and we can see what's changed. So we've changed the robot.urdf Exacro. We've added 3 other files. So I'm just going to add everything. So we can see it's staged them all ready to commit. So git commit message created core URDF and push. So that's pushed up to Git, and I'm actually going to include a link to this commit in the description so that if you've missed anything here, you can go and find those exact files and you can copy and paste things out of them and check them against what you've done if there's any troubles. Now the next step is going to be to take this robot and drop it into Gazebo, that's the simulator, and we'll be able to drive it around. Unfortunately, I think we've run out of time for this video. It's gone long enough as it is, so I'm going to stop the camera and we'll pick it up again. There'll be another video out soon. In the meantime, as always, like, subscribe. If you've got any questions or ideas, let us know in the comments, and I'll catch you later.